Okay, in today's video we're looking at average kinetic energy and average velocity in ideal gases. This is part of the unit on gases in Advanced Chemistry 30S. Kinetic energy, it's the energy of anything that is moving. Any moving object possesses kinetic energy. So in gases, when we're talking about gas molecules, gas atoms flying around their container, they're constantly moving and colliding with each other. Since they're in constant random motion, they must possess kinetic energy. In a physics class, you're given a formula for finding the kinetic energy of any moving object, including something as small as an atom or molecule. If you know the mass of that object, and if you know its velocity, you can calculate the kinetic energy with 1/2 mv squared. Now, in terms of units, the mass of the object has to be expressed in kilograms if we're going to use SI units, the International System of Units. The velocity has to be expressed as meters per second. When you do that, you'll get kinetic energy. If you look at mass times velocity squared, you'll get units of kilograms and then meters squared per second squared. That's quite a mouthful to have to say all the time, kilogram meter squared per second squared. So instead, that has been replaced with a unit called the joule. So the joule, Joule, abbreviated with just a capital J, 1 joule is 1 kilogram meter squared per second squared. Now in chemistry, we use a different formula for kinetic energy. In our gases unit, what we've got here is a formula for finding an average kinetic energy per mole, that's very important, of a gas at a given temperature. You can see that in this formula, the kinetic energy is determined by just one variable, and that's a very important thing conceptually. So temperature, measured on the absolute temperature scale, Kelvin, is the only thing that's needed to determine the average kinetic energy of particles. Now, why do we stress this idea that it's an average kinetic energy? Down here we have what's called the Boltzmann distribution of kinetic energies, and it's showing you the distribution of energies of a gas at two different temperatures. And in this little statement here, T2 is a higher temperature than T1. So let me label this as high temperature, and this is a low temperature. So what this graph is showing is that if you have, let's talk about the low temperature situation. So you have a gas contained in a container at a relatively low temperature. Some of the particles of gas that are in that container will have very little kinetic energy. Some will have higher kinetic energy. Most are going to have a kinetic energy somewhere in between those extremes. So the fraction of particles with a given kinetic energy is what's on the y-axis of the graph. The peak of the graph, right there, that particular kinetic energy at the x-axis is the average kinetic energy that we're calculating with this formula 3/2 RT. So you can see when you're at a low temperature, the average kinetic energy is less than when you're at the high temperature. And that's what our formula predicts, because as you can see here, temperature and kinetic energy must be directly proportional. When you double the absolute temperature, when you double a Kelvin temperature, you'll be doubling the average kinetic energy of the particles. So when you go from a low temperature to a high temperature, the average kinetic energy gets larger. But you'll notice a couple of other features of the graphs. When you're at a lower temperature, there's much less variation in the kinetic energies of the particles. The graph is narrower. At a higher temperature, with a greater average kinetic energy, there's also greater variation in kinetic energies. The graph ends up being wider. Now, the area under the graph, the area under the curve, in statistics, it represents the total number of particles that were in the container. So if the area underneath this tall curve would be the total number of particles at the low temperature. If all you're doing is raising the temperature, then you're not changing the total number of particles, then the area under the two curves has to be the same. If at the higher temperature there's greater variation in energies, so the curve gets wider, then the only way to have the area beneath the curve stay the same as it used to be would be to have the second curve also get shorter. So you can see there that the second curve is shorter and wider than the original curve. So that's a Boltzmann, named after a fellow by the name of Ludwig von Boltzmann, if I recall, distribution of kinetic energies at two different temperatures for gases. Now, coming back to this formula for a moment, we've already mentioned that this is the absolute, or the Kelvin temperature. You always have to use Kelvin temperatures in the gases unit. We know that the energy will come out in units of joules, but because it's per mole of gas, it'll actually be joules per mole. And then that leaves us with the ideal gas constant, this R. Okay, PV equals nRT. It's the same R from the ideal gas law. Now, in the ideal gas law, we choose a value for R based on the units of the pressure that we're using in the formula. So when we use atmospheres in the ideal gas law for pressure, we use that R is equal to 0.0821. But when we use kilopascals, we use R of 8.314. So in this formula, which version of R should we use? The key is that we're wanting to be using SI units. The version of R that's based on the SI units is 8.314. So when you're using the average kinetic energy formula, R has to be 8.314, and then the units in R will all be SI units for pressure, volume, temperature, and amount of gas. Okay, so 8.314 for R, Kelvin temperature, and your kinetic energy, the average kinetic energy, will come out as joules per mole. But again, conceptually, remember that the only thing that temperature determines here is the kinetic energy. So temperature is not about how hot or cold something is. Temperature is about the average kinetic energy of the particles. At higher temperatures, that kinetic energy is greater. Okay? We can do a quick calculation, sample problem. We know that air, the atmosphere, is made of two gases predominantly, nitrogen 78% of the air and oxygen about 21% of the air. What is the average kinetic energy for each of the gases at 25 degrees Celsius? So let's start by calculating the average kinetic energy of the nitrogen. Our formula is that the average kinetic energy per mole is 3/2 RT. So that's going to equal 3/2 times the 8.314 version of R. And then for T, we need the Kelvin temperature. So remember, you can take the Celsius temperature and you add 273 or 273.15 if you need decimal accuracy, and that's going to give you the Kelvin temperature. Since this is a whole number Celsius temperature, I'll just use 273 as the conversion factor. So that's 298 Kelvin is the absolute temperature. Now plugging that into a calculator, we'll take 3/2, which is 1.5. We'll multiply by R, 8.314, and 298. We get this large number, 3,716, and then some decimals. I'm going to round that off to 3 significant digits because of that temperature, 298. So I'll get 3.72 times 10 to the 3 joules per mole. 3.72 times 10 to the 3 joules per mole. There's the average kinetic energy of the nitrogen molecules. Now what about the oxygen molecules? If you stop and think about it for a minute, we realize it's the same formula, and the temperature is the same. R is the same, so therefore we don't actually have to do any calculation. If these two gases are at the same temperature, they have to have the same average kinetic energy. So that's also 3.72 times 10 to the 3 joules per mole. Okay, now you could switch that to kilojoules if you like by just dividing by 1,000. It'll be 3.72 kilojoules per mole. Now when you look back at those two equations that we just had for kinetic energy, there was a kinetic energy formula from physics 1/2 mv squared, this was the kinetic energy of an individual particle, an individual object. So if you knew the mass of that molecule or atom, and you knew that molecule's velocity, you could calculate its kinetic energy. The chemistry version was the average kinetic energy per mole of gas. Now on the surface, these two equations both give us kinetic energy, but the second one is per mole. So what we're going to do is we're going to say that 1/2 mv squared, the kinetic energy from physics, is going to equal 3/2 RT, the kinetic energy from chemistry, but we have one small problem. The 3/2 RT version of kinetic energy, the chemistry version, was per mole, whereas the 1/2 mv squared version from physics was of an individual particle. So what I'm going to do is I'm going to play a little game. I'm going to change the mass in the physics version, 1/2 mv squared, from just the mass of an individual particle to the molar mass, which will be the mass per mole of the gas. By switching to a molar mass, so 1/2 mv squared, now both kinetic energies, the chemistry and the physics, are now per mole. If you take that new equation and just rearrange it, you can do some algebra and solve for V. V squared, if you just look at this, the 2's on both sides cancel, and you'll end up with 3RT divided by m equals V squared. That's the average of the square velocities. And then square rooting, you'll get V is equal to the square root of 3RT over m. Now I'm going to often refer to this in our class as just average velocity, but it actually has a more statistically meaningful name. It's also called the root mean square velocity. Some people will put a little subscript VRMS, the root mean square velocity, but we're going to just think of it as an average velocity of the particles. Now, when you look at that velocity equation, which we derived from the kinetic energy equations, you'll notice that where kinetic energy was only determined by temperature, velocity, the average velocity, is determined by two variables. Temperature is there, and it's in the numerator, but it's under a square root symbol. So what that means is that temperature will influence velocity. Increasing temperature will make the velocity get larger, but because it's under the root symbol, they're not directly related. In fact, now if you want to make a direct relation, you could say that V is directly proportional to the root of T. That would be true. But for us, we'll just think of it as when T gets larger, V will get larger also. Now notice the molar mass is in the denominator. There's another variable that affects velocity, the temperature and the molar mass. But the molar mass in the denominator means that there's an inverse type of relationship. Technically, V would be inversely proportional to the square root of m. So when m gets larger, V is going to get smaller. So those two variables affect velocity. At high temperatures, particles will move faster. When they have small molar masses, they'll also move faster. Okay? Now in terms of units, we know that the temperature is going to be in the Kelvin temperature scale, the absolute temperatures. R, for the same reasons we discussed earlier, will be the 8.314 SI version of R. And then M, this is where things get a bit tricky. M has to be an SI version of mass, molar mass. And the SI version for mass is not the gram, it's the kilogram. So you have to remember that in this formula, and this is the only formula in all of chemistry in first year where this will be true, molar mass must be kilograms per mole. That means if you look up oxygen, O2, and you find on a periodic table that its molar mass is 32 grams per mole, in this formula you'd have to switch that to say it's 0.032 kilograms per mole. Okay, divide the molar masses from the periodic table by 1,000 to get grams to convert it to kilograms. And then, of course, don't forget to square root. Now you're calculating a velocity, so the velocity will have the same units it did back in that physics equation. It'll be meters per second, which are SI units for distance and time. Now we saw a moment ago a Boltzmann distribution graph for kinetic energies. Here's a similar graph, another Boltzmann distribution graph, but this time it's for molecular speeds or velocities of different noble gases. So the x-axis shows us speed, average speed, this V from our formula above, and on the y-axis we have probability, or you can think of it as number of particles or fraction of particles in a container. We see these same curves, same shaped graphs that we saw earlier. Their name in statistics, by the way, they're referred to as normal curves. That shape of graph, it's called a normal curve. Sometimes it's just called a bell curve. It kind of looks like a bell-shaped curve. All right, so now you'll notice of these four gases, helium, neon, argon, xenon, if you looked at a periodic table, you'd see that helium is at the top of that family. It has the smallest molar mass. Given that it has the smallest molar mass, its average velocity, which would be here at the peak of its curve, is greater than the average velocity of any of the other gases. Neon would have the next greatest, argon is next, and of these four gases, xenon has the lowest average velocity because its molar mass is the largest. That assumes that the gases are all at the same temperature. You'll notice we also have a similar effect going on in terms of variation. The smaller molar mass, helium, has a larger variation in its speeds than the very large molar mass, xenon, which has a very narrow variation in its speeds. So let's use that velocity equation in a problem. You can pause the video if you like and try this. Calculate the root mean square velocity, the average velocity, of carbon dioxide molecules at 30 degrees Celsius. Then a second question, at what temperature would helium atoms have the same average velocity as these carbon dioxide molecules at 30 degrees Celsius? So the first part of the question is just a straightforward plug things into our formula. So V, the average velocity, was equal to the square root of 3RT over molar mass. So that's going to equal the square root of 3 times 8.314, the SI version of R. The temperature in Kelvin, we take this Celsius temperature, 30 degrees, we add 273, and we get 303 Kelvin. And then the molar mass of carbon dioxide, if you look it up on a periodic table, it'll be 44.01 grams. But we need to use kilograms, so we'll divide that by 1,000, and we get 0.04401 kilograms per mole. Now plugging that into our formula, grabbing a calculator, we'll get the square root of 3 times R times T divided by the molar mass, 0.04401. And that's going to equal 414, I'll keep 3 sig figs, meters per second. So 414 meters per second. Notice that these particles move very fast. 414 meters, almost half a kilometer, in 1 second. That's an amazingly high velocity. And yet, we know from everyday experience that gases tend to diffuse relatively slowly through the air. If you insert a gas into a room, it doesn't spread out into the room instantaneously, as this velocity would suggest. Instead, it takes a long time to slowly spread out through the room. How do you explain that? How can gas particles be moving this fast when gases tend to diffuse through their containers relatively slowly? The answer is that the gas, as it's diffusing through the container, is not diffusing into a vacuum. It's not traveling through an empty space. the air in the room, or the air in a container, is full of particles already. So here's nitrogen and oxygen atoms, or molecules rather. If you put carbon dioxide into the container, the carbon dioxide molecules move super fast. Let's suppose here's a carbon dioxide molecule. It travels super fast, collides with another particle, a nitrogen molecule perhaps. When they collide, it changes direction, and then it moves super fast, 400 meters per second, but it collides immediately with another oxygen molecule. It changes direction randomly, and then moves over and collides with another particle, and then changes direction randomly and moves again to collide with another particle. That constant changing of direction as it's colliding with gas particles in the container is what explains why, even though it's moving super fast, it takes a relatively long time to diffuse through the container, because it's constantly changing directions randomly as it diffuses. Now, the second part of the question said, suppose we have helium atoms and we want them to have the same average velocity as these carbon dioxide molecules. Then what temperature would the helium atoms have to be? Okay, so what we'll do is we'll take this average velocity, 414 meters per second, and now this is the helium average velocity. So that's going to equal the square root of 3 times R, 8.314, and we're wondering at what temperature, so let's say T, and then divided by the molar mass of helium. Helium's molar mass on a periodic table is 4 grams per mole, so this will be 0.0040 kilograms per mole. So I'll take 414, I'll square that to get rid of the square root symbol. I'll multiply this by the molar mass, 0.004, I'll divide by 3, and I'll divide by R, and I get 27 Kelvin. So T is equal to 27.5, I'll keep 2 significant digits, 27 Kelvin, a very low temperature. Subtracting 273, 27 minus 273, we get negative 246 degrees Celsius. So at this very, very low temperature, the helium atoms have the same average speed as carbon dioxide molecules moving at 30 degrees Celsius. The reason for that, of course, is that helium's molar mass is much, much smaller than the carbon dioxide's molar mass. All right, we'll finish with a conceptual problem. So don't use a calculator for this. Let's put our calculators away. We have 4 identical balloons. The first one, you may not be able to see the labels, contains nitrogen gas. The second one contains hydrogen gas. The third one contains argon gas. And the fourth one contains methane gas, CH4. We're told that the balloons all have a volume of 2 liters, so their volumes are all the same. They're all at 20 degrees Celsius and 100 kPa. So their volumes, their temperatures, and their pressures are all the same. So based on that, which balloon has the particles with the greatest average velocity? See if you can pause the video and figure that out. Alright, so we know that average velocity, V, is equal to the square root of 3RT over molar mass. So temperature and molar mass affect the velocity. But the temperatures are all the same. If the temperatures are all the same, then only the molar mass will differentiate the velocities. So since molar mass is in the denominator, we want the greatest average velocity, then we want the gas whose molar mass is smallest. So looking at those 4 choices, nitrogen's molar mass is 28 grams per mole, 2 times 14. Hydrogen is 2 grams per mole. Argon, I don't recall, but it's larger than that. And methane is about 16 grams per mole. So of those choices, hydrogen is the one with the smallest molar mass, therefore it's the one with the largest velocity, the greatest velocity. which balloon has particles with the greatest average kinetic energy? Pause the video and see if you can answer that. Well, average kinetic energy, we know, is equal to 3/2 RT. So the only thing that determines average kinetic energy is temperature. Since the temperatures are all the same, all four balloons must have gases with the same average kinetic energy. None of them are greater than the others. So all of the balloons are equal. It's a bit of a trick question. The third question, which balloon has the greatest number of particles, atoms or molecules? Well, looking back, we notice that V, T, and P are the same for the four gases. If I think about the ideal gas law, PV equals nRT, I can rearrange that to say N is equal to PV divided by RT. So we could calculate the number of moles in each balloon. But looking at this for a moment, the P is the same, they're all the same pressure. The V is the same, they have the same volume, and the T is the same, they have the same temperatures. R is a constant. So if we were to calculate how many moles, we would discover that all four balloons have the same number of moles of gas. Since they have the same number of moles of gas, that means they have the same number of particles in the container. There'll be the same number of nitrogen molecules as there are argon atoms in these balloons. So N has to be the same because these variables PV and T are all the same. And finally, which balloon has a gas with the greatest density? See if you can figure that out. The greatest density. Well, I remember we derived a density formula from the ideal gas law. So P times V was equal to nRT, but moles was equal to mass divided by molar mass. And little m, mass, divided by big M, molar mass, gives me moles. So we put those together and we get P times V equals mRT over molar mass. And then looking at that, we have an M mass here, and we have a V volume here, so we can rearrange that to find density. Density is mass divided by volume. So to get mass divided by volume, we would multiply both sides by the molar mass, we would divide both sides by RT, and then we would divide both sides by V. What we get in the end is P times M divided by RT. So there's a formula for finding density of a gas. So the density is the pressure times the molar mass divided by R and T. All four gases have the same pressure, the same temperature, and R is the same for all of them. But molar mass is not the same for the four gases, so they do not have the same densities. If I want the one with the greatest density, molar mass in the numerator here, so the gas with the largest molar mass will have the largest density. Of those four choices, argon was the one with the greatest molar mass, so argon will have the greatest density of those four choices. Alright, so there's a quick review of kinetic energy and velocity of gases with a few problems to practice them. Okay, the key is to remember that temperature is the only thing that affects the kinetic energy, whereas temperature and molar mass affect velocity. Also remember the units. Temperature is always going to be in Kelvin. We always use the SI version for R in these formulas for kinetic energy and velocity. And in the velocity equation, molar mass has to be given in kilograms per mole.